Welcome to Lecture 10, Computing Systems. We're finally looking inside the CPU. What we're going to consider this week is the instruction cycle and how instructions are actually carried out by the CPU. Key steps in this process are that the CPU needs to fetch the instruction from memory. It has to decode the instruction. It has to access memory again to access any data it requires. It has to execute the instruction, and it has to store the result. Collectively, this is known as the instruction cycle, or sometimes the fetch, execute, decode cycle. CPUs have a number of different elements within them. The program counter stores the memory address of the next instruction to be executed. The instruction register is where we can fetch instructions and store them in the instruction register so that the processor can then carry out that instruction. The arithmetic logic unit is one of a number of data processing units that might exist in a CPU. So other CPUs may also have floating point units, and they may have multiple arithmetic and logic units and multiple floating point units. We're only going to consider the simple form of CPUs just now, with just one ALU. Memory address register stores the current information about the current address of memory we're going to be using for reading and writing instructions and data to and from memory. It tells us which memory address, which bit of memory is currently active for reading or writing. The MBR, memory buffer register, sometimes also known as the MDR, memory data register, stores a copy of the value or the contents to be read from or written to memory. And processors also typically have a number of data registers. Say, for example, it has 16 registers. They may be register 0 through to register 15. And these may be used to store instructions, more commonly just used to store data that the CPU is going to operate on. And this is a schematic based on a diagram by Alan Clements that you can get from his website of the insides of a CPU and how data is passed around inside a CPU. So this obviously doesn't show you the actual circuitry, but it gives us a sort of high-level schematic view of how values are passed around inside the CPU. For example, to fetch an instruction, the program counter stores within it the memory address of the next instruction to be read. So that has to be passed to the memory address register. As soon as that's done, the program counter value can be incremented so that it now is going to point to the memory address after that for reading the following instruction. Once we have a value in the memory address register, that can be used to switch on in memory the active block of memory that stores the current instruction. And that instruction can then be copied into the memory buffer register, from where it can then be copied into the instruction register, ready to actually be executed. Other data paths may allow values from memory to be copied into the memory buffer register, passed into different registers for processing, passed into the arithmetic logic unit, for example, for doing different additions, for example, for adding two values together, and then potentially passed back to the memory buffer register and returned to store the result in memory later. There are a range of different architectures. The schematic we've seen is a very simple, basic architecture. Current architectures can be quite complicated, but most modern architectures will have a large number of different processor registers. Most computation is on the values in the registers. So a lot of the work of the CPU is simply moving values from memory into and out of the registers. Modern processors will often have a general purpose registers and also a general purpose cache. So that because accessing the main memory, the RAM that's stored in another bit of chip elsewhere inside the computer, that takes quite a long time. So most CPUs actually have a local memory cache, say anything from 16K to 4 megabytes or 16 megabytes or more. And that allows it to store part of the program it's running on the CPU and to operate and run that bit of the program very, very fast because it's all on the CPU. Some processor architectures may have special purpose registers, so there may be registers that are for very specific uses, and they may also have separate cache for instructions and for data. There's a range of different architectures out there. I'm not really going to be discussing stack registers in this class, stack-based CPUs in this class, really just looking at the CPU ones. Older processors often used something called a stack instead, and so you could store values in the stack, and when using the stack you can add values to the top, and when you're reading values off, you read off the most recent values first. And there's a number of reasons why these have kind of fallen into favour for CPU design, but they were used quite a lot in earlier designs. So to fetch the next program instruction, we can also look at this using something called register transfer language. And here you might recognise these names. These are the names of some of the different components of the CPU. So in this case, to fetch the instruction, we're going to copy the value currently stored in the program counter over to the memory address register. We're then going to increment the program counter, in this case by 4 bytes, so that it points to the next instruction. So this is a 4-byte, a 32-bit processor. So incrementing the program counter to point to the next instruction and storing that value in the program counter. Now with this double brackets, instead of copying the value stored in the memory address register, we're using that value to access memory. So we're going to copy the value stored in memory pointed to by the memory address register. So we're copying the value from memory into the memory buffer register, and then finally copy value from the memory buffer register into the instruction register. So we go through those 4 steps for each instruction as we're trying to read the instruction from memory and have it into the instruction register ready for execution. There are a range of different instruction types that a processor may try and carry out. Arithmetic and logic operations, including adding and subtracting and multiplying, dividing, ANDs or XORs. We might load values into the CPU from memory or store them back in to memory from the CPU. And we can compare values, so is value in register 0 equal to or greater than the value stored in register 1, for example. And based on the result of some comparison, we may have some branch or control operation. So we may have jumps or conditional branches. And that's useful so that we can implement loops and structured programs, and also functions and procedures. And we have a way of implementing those on the CPU. The instruction that gets copied into the instruction register will consist of 2 parts. The opcode is really a pattern of 1s and 0s that is unique for each different instruction. So the add instruction will have a particular pattern of 0s and 1s that means add. And the subtract instruction will have a slightly different pattern of 0s and 1s that means subtract. So a particular bit pattern will specify a particular instruction. But the instruction also has the operands, so we know we're going to add something, but what are we adding? So the operands tell us what are the values that are going to be added or subtracted or otherwise operated on. And instruction sets may have used 2 or 3 operands to specify the data to be used for the instruction, potentially also where to store the result. So here are some examples. Add R1, R3, R2. It's going to add R3 and R2 and store the result in R1. Or we might use #2 to indicate that we're going to add the number 2 to something else. So instead of adding a number that's stored in the register, we're going to add the actual number 2. And with move, it allows us to store a value in a register, so we could copy from one register to another, for example. obviously do multiplies and a whole range of different arithmetic operations. Final two instructions here show us a branch. So we have a comparison. We're comparing the value stored in register 0 and the value stored in register 1. And if they are equal, we're going to jump to a bit of the program called label. So in assembly code, we can label a different bit of the program, and the BEQ means branch if equal, and so that will branch if the result of the previous instruction indicated that the result was an equal result from the comparison test. So it's using the result from the previous instruction to decide whether or not to branch in the next instruction. The actual instructions that are provided in any processor will vary by processor, so the particular patterns of zeros and ones and what they mean and what each instruction is will vary by processor. But any one family will have a common basic instruction set. So in the Intel architecture, for example, you can run a program written for Windows, and it's been compiled and it's in machine code, and you can run that on any Windows PC because they have the same basic instruction set. Later versions of the processors may have additional instructions that earlier chips don't have, and they may process things slightly differently or have different speeds of performance, but there'll be a sort of basic core that they have in common. Some instruction sets, again for example the Pentium instruction set, include features that allow some individual instructions, some machine code instructions, to be quite complicated in terms of what they do. In terms of operating in values that are drawn from different memory addresses and storing the result on another memory address, all in one operation. So instead of having to have different machine code instructions to get different bits of data, put them in registers, then do the operation and then store the result, we may have an instruction set that allows us to combine several of those steps in one instruction. Instruction sets that allow this are generally referred to as CISC, Complex Instruction Set Computing architectures. Now, the Pentium processor range is obviously highly successful, but there are some issues with the use of CISC. It was kind of driven by this need or perceived benefit of having machine code instructions that could be very complicated, and therefore when you compile a high-level language program, you'll have almost a one-to-one match between the high-level language instructions and the instructions that the machine itself can operate on and can do. And so almost any high-level language instruction is going to turn out to be just one single machine code instruction to do that, instead of having lots of machine code instructions for each high-level language code instruction. The downside is that you end up with some complicated chip designs, and there's some expensive and complicated circuitry in there for some of the commands and instructions that are very rarely used. And this complicated circuitry and the decode circuitry complexity will affect the performance. And so a single machine code instruction might take several clock cycles to complete. So the speed of the processor is measured in a clock speed of so many gigahertz or megahertz, how many million or billion times per second the processor is able to do something. But a single instruction, because it's so complicated, might take several clock cycles to complete. And different instructions might operate at different speeds as well, which can also complicate your design. The alternative approach is termed reduced instruction set computing, RISC. And one of the core ideas here was really to limit the processor to more basic operations, and that the simpler decode circuitry would allow for higher processor speeds. There would be a more fixed time to execute any instruction, so that it's more predictable how long it takes to operate different instructions, because they all operate at the same time. And that while you might require more than one operation in a RISC chip to do something that can be done in one machine code operation in a CISC chip, the overall processor speed is faster, and by using a compiler that optimizes the program for the processor, you can actually still get a better performance with a RISC chip than with a CISC alternative. That's the principle anyway. The importance of the compiler actually led to an alternative acronym for RISC, which was Relegate Instruction Stuff to the Compiler. That really emphasised the important role that a good compiler and advances in compiler technology have in developing and supporting the RISC processors. So it's not just about the processor itself, but it's also about the compiler that turns a program that you've written into a program that the machine can understand, but actually reorders the instructions and it optimizes things for the processor specifically. An example of one of the RISC innovations that's also come into CISC since, we can see in the following few slides. So for example, if we consider how many clock cycles it takes to perform one instruction. So an instruction has to be fetched, that might be one clock cycle, has to be decoded, another clock cycle, executed, we need to access memory and we need to write back the result. So it might take about 5 clock cycles per instruction. So if we complete one instruction before we read the next one, we have 5 clock cycles per instruction. But most of the time, most of the circuitry in the chip is actually doing nothing. So while we're fetching the instruction, the decode circuitry, the execute circuitry, the memory and the write-back circuitry, these are all just idle, not actually doing anything while we're fetching the next instruction. So an alternative idea is to use a pipelined architecture to take benefit of this, to try and have all the parts of the processor doing something at the same time. Most of the time we can do this effectively because most of the time the next instruction that we're going to need is going to be found by just incrementing the program counter and just grabbing the very next instruction. Sometimes when we've got a loop or a branch or an if statement, we might accidentally pick the wrong instruction next. But there are ways in which processors can try and minimise the cost of any misprediction there. And this is pipelined execution. So we fetch our first instruction, and as soon as we start decoding that, we're ready to start fetching the second instruction, and so on. So that by the time we're ready to write back the first instruction, we're ready to fetch instruction number 5. And when we finish writing back instruction number 1, when we finish instruction 1, we're ready to start fetching instruction 6. So potentially, we're completing the instruction every clock cycle. As the first instruction completes, the 6th instruction enters the pipeline. So you can think of it as a sort of pipe almost of instructions coming through. And as soon as one's finished, the others are all in the pipeline. The next 4 are in the pipeline. And then the instruction number 6 is just ready to enter into the pipeline. Over time, CISC has evolved and it has embraced many of the features that originally developed as part of the RISC design. For example, pipelining support. You can also get very powerful at optimizing compilers for the Intel architecture, because it's a popular architecture. People are also interested in developing compilers that can really boost the performance of your program. The CISC processor types continue to dominate desktop PCs and laptops, and that's largely, I think, with a compatibility with the existing user base and existing software. It would be hard to sell someone a new PC or a new Mac if you told them, by the way, none of your current software will run on it. You'll have to buy all new software, and also for the development companies to say to all the development companies, now you need to write new versions of all of your software for this new computer architecture. People would presumably continue to buy the machines that run the software they want, and the software developers would continue to create software for the machines that people actually have. So it's very hard to shift over the sort of desktop architecture to a new processor type because of the huge effect of the installed user base. On the other hand, RISC dominates the mobile, embedded and entertainment sectors. So ARM devices are found on mobile phones and a huge range of mobile devices as well as embedded devices. And the PowerPC architecture, in different forms and different processors, has found a home in all 3 of the current mainstream home consoles. The Xbox, PlayStation and the Wii all have PowerPC based processors. There's a lot more further reading, particularly the Alan Clements website goes into more detail on the fetch execute cycle. Next week's class is on more human stories, and again some recommended reads. There's lots of good bios, Wikipedia and elsewhere, and a lot of interesting characters who've had a lot of input into the history of computing. So not all of these are 20th century usual spot, but Alan Turing, John von Neumann, Vannevar Bush, Alan Kay, and so on. Lots of interesting characters and some of them quite interesting stories behind them and how they got involved in computing. The title image is by myself. The CPU data address path schematic shown in this slide was one I created. It was based on an original by Alan Clements. You can see on his website. And similar diagrams are also available in his Principles of Computer Hardware book. Thank you.